All right, good day, everyone. Welcome to Insight Tutorials. So today we're going to be going through certain revisions. Perhaps you're a 100 level student doing physics 102, that's general physics 2, and you're thinking how best to prepare for your exams. We are going to actually look into the revision aspect of this, and in that revision, I'm going to take you through a lot of practice questions. We'll solve them. The one that are actually theory based, we'll solve them CBT standard. All right. And those questions are going to be cutting across the listed topics here. See, magnetism, electricity, and electrostatics. We're going to be looking at special relativity question from quantum physics. There will be question also from modern physics, electromagnetic induction. We're going to go into atomic physics, alternating currents circuits. Sorry, right there, that's alternate current circuits. We're going to go into nuclear physics, and then we're going to look into capacitance. All of those, because of our questions, you will see where these particular questions are drawn from, but of course they'll be from this very topic. So while we kickstart today, I remain your tutor for today, Peter Ogbaji. Let's go right away into this. Thank you. All right, it happens that we have a question here for us, and this question is actually from magnetism under the subtopic you refer to as force on a current carrying conductor in a magnetic field. All right, and it happens that the formula that will aid us in solving this particular question is stated here. The question says a 2-meter wire carrying a current of 3 ampere is placed in a uniform magnetic field of 0.70 Tesla. If the wire makes an angle of 40 degrees with the magnetic field, what is the magnitude? We're talking about the size. Now, what's the magnitude of the magnetic force on the wire? So we have to look for the force on this wire. Now, F is actually the force on this particular wire, which is measured in Newton. And B here is the magnetic field density on that wire, which is measured in Tesla. I is the current that is flowing through that particular wire, measured in ampere. And L is the length of that wire that is placed in that magnetic field, that is measured in length. And sine theta here, the angle here, is the angle between the direction of the current and the magnetic field. So we're going to go straight into solving this particular question. But before we do that, it's very advisable that you write out your variables. So we're looking for the force. Now, what is our magnetic field in this question? What's our magnetic field in this question? It's given as 0.70 Tesla. And then in terms of our current, which is in ampere, we have 3 ampere. And then we have our length as 2 meter. We have the angle between the direction of the wire and the magnetic field as 40 degrees. Now, with this given, we're going to actually impute it into this formula and then get our answer. So it happens that the force is given as this magnetic field of 0.70 times our current of 3 times our length of 2 times sine 40. So I'm going to make it on my calculator. So we have 0.70 times. So this alone is 0.0. This is 4.2 times. This is sine 40. So what is sine 40? We all know that sine 40 is 0. So this is 4.2 times 0. Sine 40 is 0.64228 approximately. So if we multiply that by 4.2, we have 2 points. We have 2.699. So approximately it is 2.7 Newton. So it happens that option D is a correct answer. We'll go to the next question. All right, question 2. We have it that we're told that a charge of magnitude 1.0 times 10 to the power of minus 5 coulomb produces an electric field intensity of 9.0 times 10 to the power of 4 Newton per coulomb at a certain point. Calculate distance from the charge. So this is actually a question from electrostatic. And this question is actually drawn from electric field due to point charge. So electric field is given as K times Q all over R square, where E is the electric field intensity, that is measured in Newton per coulomb, and then K is the Coulomb constant, which is 9.0 times 10 to the power of 9 Newton meter square per coulomb square, and then R is the distance from the charge, which is measured in meter. So from what we are given, we are asked to find the distance. We to calculate distance from the charge. That means we're going to make our R the subject of the formula. But let's do that before. But before then, let us write out the values we have. Remember that our K is a constant value of 10 raised to the power of 9 Newton meter square per coulomb square. And then we have our charge given to us as 1.0 times 10 raised to the power of -5 coulomb. And then we are told to find our distance. And then our electric field was given to us as 9 times 10 raised to the power of 4 Newton per coulomb. So we have to look for our distance. Now, in doing that, we're going to make our R the subject of the formula. So that means we write electric field intensity times the distance in its squared times the constant and the charge. We write R square equals to, this is KQ all over E, where R is going to be the square root of our K and the charge all over the electric intensity. Having arrived at this particular formula, we're going to substitute our value into this, and then we'll get our distance from the charge. So our charge is 9 times 10 here, 9 times 10 raised to the power of 9 times. Our charge is 1 times 10 raised to the power of -5 all over our electric field intensity is 9 times 10 raised to the power of 4. Okay, so we're going to do, if we're doing that, in essence, it's going to be this times this is going to be 9 times 10 raised to the power of 4 all over 9 times 10 raised to the power of 4. Because, of course, according to standard form, this will become 9 raised to power 9 times 10 raised to power 4. So what we have here in essence is that if you do this divided by this is 1, and the square root of 1 is 1. So it is 1.0 meter. That is the distance from the charge, giving the electric field intensity as that. So that was that option A is correct. We'll go to the next question. All right, the third question we have here to deal with says that a meter stick of proper length 1.0 meter moves at 0.6 C relative to an observer. Calculate its measured length. Now, the formula, this particular question is from special relativity, and the subtopic is length contraction. There's a general formula for solving that, all right? All right, so the formula that will guide us in solving this is the contracted length is equals to the proper length times the square root of 1 minus the velocity of the object all over the speed of light, all in their squared form. So we have it that our proper length, as given in the question, is 1 meter. And then our speed of the object, the velocity of the object is 0.6 c. This c is simply the speed of light attached. And then we are told that then the next one is the speed of light, which is approximately 3 times 10 raised to the power of 8 meter per second. So we're going to look for the proper length, having gotten all this. So in solving that, it will be that the length is equal to our LO is 1 meter times the square root of 1 minus the speed of the object is 0.6 c all in its squared all over c squared. Now, my advice to you is you don't need to actually impute this particular speed of light into this equation. Reason being that you will see why I say you should do that, because if we go down, we're going to have our contracted length equals to 1 times. and this is the square root of 1 minus. If we solve for this particular bracket, we are going to have 0.6 times 0.6 and then c times c. So we'll have 0.36 c squared up here all over c squared. Now it is easier for you to just simply cancel out this speed of light and cancel out this speed of light since they are actually having the same exponent, all right? So L is 1 times, and this is 1 minus, this will cancel this. What we have here now is 0.36. Our proper length is still the square root of this one is, you know, is insignificant. So this is 1 minus 0.36 is 0.64. So the square root of 0.64, it happens that our proper length is 0.80 meters. So the correct option is option D. So the next question. So we have a question here, and this question particularly is still from special relativity, but under what we call relativistic energy, or relativistic total energy and Lorentz factor. There's actually a relationship with that. Now, there are two formulas that we really need to be able to solve this question. Now, in a normal sense, the total relativistic energy is given as the Lorentz factor times the mass at rest times the speed of light in its squared, right? And the speed of light in its squared. But we will not be able to solve this question if we've not found this particular Lorentz factor. So we have to find the Lorentz factor first. Why? We have the mass, and the speed of light, we know it's constant as 3 times 10 raised to the power of 8 meters per second. So we have to find what? The Lorentz factor first before we apply this. And the formula for the Lorentz factor in itself, the Lorentz factor is 1 all over the square root of 1 minus v squared all over c squared. All right? And we all know that so what we have here now, from what we are given, we have our mass, but to be able to solve this, we need the speed of that particular particle, which is 0.8 the speed of light. All right, so we're going to have it that our Lorentz factor is 1 all over the square root of 1 minus our v square is 0.8 0.8c, so sorry, 0.8c all in its squared all over c squared. All right, so Lorentz factor is 1 all over. Now we have the square root of 1 minus. Now this is going to be 0.8 times 0.8 times c, all right, because this square will apply to the two numbers in this bracket. So we're going to have 0.8 times 0.8 should give us 0.64, and c times c should give us c squared all over c squared. Now from what we have here, we can actually cancel out this speed of light and cancel out this speed of light, so that we're left with 0.6. So we'll continue from here. Lorentz factor is 1 all over the square root of 1 minus 0.64. Now Lorentz factor is 1 all over the square root of 0.86, because if you do 1 minus 0.64, you have 0.86. So Lorentz factor is 1 all over the square root of 0.36 is 0.60. And so 1 divided by 0.60 is 1.667. So it happens that the Lorentz factor is 1.667. Now we have our Lorentz factor. So for us to be able to find the total relativistic energy, we need to apply this formula. And in this formula, we already have our Lorentz factor as this. And then our mass was given as 0.5 in its proper unit, which is kilogram. And though we know the speed of light, so with that we can find our total relativistic energy. So total relativistic energy is equals to the Lorentz factor, which is 1.667 times our given mass of 0.5 times the speed of light, which we know as 10 raised to the power of 8. this is squared. Now, it happens that, okay, so 3 times 10 raised to the power of 8 in its squared, it gave us, so we have 1.667 times 0.5 times. If we multiply that, we're going to have 9 times 10 raised to the power of 16. And if we multiply 1.667 times 0.5 times 9 times 10 raised to the power of 16, we're going to have our total relativistic energy as 7.5 times 10 raised to the power of 16 joule. So it happens that option C is a correct answer to this very question. Okay. This is another question from special relativity. As you can see, they say a space prop has a proper length of 18.0 meter. What length is measured when it moves at 0.7 the speed of light? These are our options, so we'll find out which is correct. You can attempt it before we solve this. What do you think will be the correct stuff? Let's solve and see. All right. So we have our proper length, our contracted length equals to our proper length, all into the bracket of 1 minus the speed of the probe times the speed of light. And from what we have, we're given our proper length as 18. So our proper length is 18 times 1 minus the speed of light was given as, the speed of the probe was given as 0.7, the speed of light, all over c squared. Now this is 18 times 1 minus, if you multiply this, you're going to have 0.49 c squared all over c squared. It happens that we cancel these two instead of putting it in numerical value. This 18 times, and this is the square root of 1 minus 0.49. So 18 times the square root of, now 1 minus 0.49 is 0.51. So the square root of 0.51 is given as 0.714. And if we multiply that, our proper length, 18 times 0.714, our proper length will be approximately 12.85 meters. So it happens that option B is the correct answer to this very question. All right, we have a question here, and this particular question is drawn from quantum physics under photon and wavelength, all right? Photon energy and wavelength. And there's a formula that connects when you're finding the wavelength of, when we're told to find whose wavelength is this, calculate the energy of a photon. Now there's a formula that connects that, all right? So the formula we're going to apply in solving this question is the photon of an energy is equals to the Planck constant times the speed of light all over the wavelength. All right, is the formula we're going to apply in solving this particular photon related question. And we've already been given our Planck's constant as 6.6 times 10 to the power of negative 34 joules second. And we have the speed of light, which you know is a constant. We have our wavelength also given as this. We are told to find the energy, right? So we're going to just substitute that into this equation. So we'll have it that this is 6.6 times 10 raised to the power of negative 34 times 3 times 10 raised to the power of 8 all over our wavelength, which is 1.5 times 10 raised to the power of negative 26. So we could go ahead in doing this in our calculator, and what we have in essence here is 6.6 times 10 raised to the power of negative 34 times 3 times 10 raised to the power of positive 8. That one that will have 1.98 times 10 raised to the power of negative 25 all over 1.5 times 10 to the power of minus 26. And so if we do 1.98 times 10 raised to the power of minus 25 all over 1.5 times 10 raised to the power of minus 26, it happens that our answer is 13.2 joule. So option B is correct. All right, so this is a question from electromagnetic induction, and we're going to calculate energy stored in an inductor. All right, and there's actually a requisite formula for solving this. So our question says that we should calculate the energy stored in an inductor of inductance 10 millihenry carrying a current of 2 ampere. All right, the formula for calculating energy stored in an inductor is given as U is equals to half times our inductance L, which is measured in Henry, times our current in its squared form, right? So it happens that our inductance was given to us as 10 millihenry, and then our current was given as 2 ampere. We could supply. Now, before we do that, before we solve this, we have to do a conversion here. Our inductance is to be measured in Henry, not millihenry, okay? So we're going to say it will be 10 times 10 raised to the power of negative 3. That's how you convert from millihenry to Henry. You attach 10 raised to the power of the negative 3 power, okay? And this to give us 0.01 Henry. With that conversion being done, we can find our energy stored as 1 over 2 times 0.01 times 2 raised to power 2, all right? So our stored energy is 1 over 2 times 0.01 times 4. It happens that 2 can go here, 2 can go here 2 times. So our stored energy will be 0.01 times 2 gave us 0.02 joule. So this is the energy that is stored in this particular circuit. And so with that being said, our correct option is option A. Okay, so this question is actually from electrostatics. It has to do with force and Coulomb's law, right? So we're going to deal with this particular question now. All right, so the question says calculate the force of repulsion between two electrons. Take note, these electrons are negatively charged. Now, two electrons, each of charge magnitude 1.6 times 10 raised to the power of negative 19, separated by 1.0 times 10 raised to the power of negative 10 meters. Now, for us to be able to solve this question, remember we have a uniform charge for the both of them. So this is a formula. The force is equal to the Coulomb constant times the first charge times the second charge all over the distance between those charges in its squared. All right. Now we have it that this particular force, for us to find, they say each of charge. Now this is the magnitude of 1.6. That's to say both the magnitude of the first, the magnitude of the second charge are both 1.6, since they have the same they are both of two electrons and have the same magnitude. So what we're going to do in essence is that our distance between them was given as 1.0 times 10 to the power of negative 10 meter. And then we have Q1 and this is Q2. They say they have the same charge, you understand? And if you do Q times Q, it's going to be Q squared, right? So what we have here now is Q squared. So in essence, what we have here, we're going to square it, which is going to be 1.6 times 10 raised to the power of minus 19, all in squared, right? All in squared of the Coulomb. And K, which is a Coulomb constant, most of the times can given as 8.89, but approximately we could write it as 9 times 10 raised to the power of 9 Newton meter square per Coulomb squared, right? So what we have here now is we could solve for this, for the force. So force is given as 9 times 10 raised to the power of 9 times. So we're going to do 9 times, this is, so let us, this is 1.6 times 10 raised to the power of minus 19, all in its squared, all over Our distance was given to us as 1.0 times 10 to the power of negative 10, all in its squared. Now, we'll continue solving from here. So our given force is equal to, so let's say this is 9. Let's say, right, this is 9 times 10 raised to the power of 9 times. So 1.6 times 10 to the power of negative 19 in squared is given as 2.56 times 10 raised to the power of negative 38 all over our 1.0 times 10 raised to the power of minus 10 in its squared is 1 times 10 raised to the power of minus 20. All right, so we're going to multiply this all at once. 9 times 10 raised to the power of 9 times 2.56 times 10 raised to the power of negative 38 divided by 1 times 10 raised to the power of minus 20. So having gotten that, we have it that our force is 2.304 times 10 to the power of negative 8 Newton. Approximately, we can write just 2.3 times 10 to the power of negative 8 Newton. So there's actually a force of repulsion. Reason being that there's actually a force of repulsion. Reason being that these two charges are like terms. Remember the law of electrostatic? If they are like terms, they repel. If they are unlike terms, they attract. So that's the force of repulsion between these two electrons separated by this distance. All right, we have a question here that says which pair is isotonic, and look at all the elements that are listed and their various options. All right. Now, I quickly wrote down something here that is very, very important for you to note. For us to be able to answer this question, we must understand these three keywords. All right. There's what referred to as isotopes, there's isobars, and there's isotones. And when we talk about isotope, it's simply elements of the same atomic number, right, but different mass number. And isobar is the opposite of isotope. It is same in its mass number, but different in its what? Atomic number. Why isobars are simply when the neutrons of the elements are the same. When neutrons are the same, neutrons of elements are the same. So for us to be able to get that, looking at option A, it has the same atomic number, but different mass number. Obviously, it is not isotonic. It's rather isotopic, right? Option B is having the same atomic number again, but different mass number. This is also isotopic, not isotonic. Option C has the same mass number, but different atomic number. This is isobar. It's an example of an isobar. And this perhaps is going to be the correct answer. How are we going to prove that? Let us say that this is N is equals to A minus Z, because we want to check if the two elements, if their neutron will be the same. All right. So in doing that, this N is the neutrons, A is the mass number, and Z is the what? Atomic number. So this particular first element for N that has 13 and 7, we're going to say that the neutron is, the mass number is 13 minus the atomic number, which is 7, and this is going to give us 6, right? For the carbon, so let's say for the carbon with 12, so the neutron is going to be, the mass number is 12, the atomic number is 6, and that another is 6. If you notice 6 and 6, so this is the only option that is what? Isotonic, when the neutrons are all the same. Hope you get that. All right, so we are given a question here, and this question is actually from alternating currents, and the particular topic where this is drawn from is actually transformers. All right, and yeah, transformer turn ratios and the step down transformers. So we are given this particular question that a primary coil of an ideal transformer has 1,200 turns and is connected to 240 volts. If the secondary voltage is 12 volts, calculate the number of secondary turns. Now, the general formula we're going to use in solving this is Vs all over Vp equals to NS all over NP. Now, what does this mean? This is the voltage of the secondary coil, is the voltage of the primary coil, is the number of turns of the secondary coil, is the number of turns of the primary coil. All right, so we're going to apply that formula in solving these very questions. But very importantly, we're going to write out our variables from this very question. Now, they said a primary coil of an ideal transformer has 1,200 watt turns. So what that means is the number of primary turns, first of all, is 1,200. Remember, we have to look for the number of secondary turns. So we don't know what is our number of secondary turns. That's what we're looking for. So we're given our voltage of the secondary coil as what? 12 volts. So our Vs is 12 volts. And then this primary coil of an ideal transformer has 1,200 turns and is connected to 240 volts. So that is going to be our primary voltage. So our Vp is 2,240 volts rather. So for us to solve this in a very simple manner, we're going to cross multiply so that we can make a number of turns for secondary subject to the formula. So Ns times Vp equals to, if we cross multiply, we're going to have Ns times Vp, which is equals to what? Vs times Np. Now we're looking for a number of turns for the secondary coil, which is equals to Vs Vp all over, Vs Np all over Vp. So our number of secondary turns is going to be, our Vs is 12 volts, 12 times our number of turns for the primary coil is 1,200 all over 240, which is our voltage, our primary voltage. So the number of turns secondary is going to be 12 times 1,600 divided by 240. So our answer is 60 turns. So the secondary voltage is lower than the primary voltage, all right? So the device is a step-down transformer. It's a step-down transformer. So we'll go to the next question. All right, so we're giving questions here. The first one says, which statement about electric field lines is correct? A says they cross one another at several points. B says they originate from negative charges and terminate on positive charges. C says they originate from positive charges and terminate on negative charges. D says they form closed loop around stationary charges. Now, the key concept you need to understand is that electric field lines actually shows the point from where the positive charge, or the direction where the positive charge is actually moving towards. All right. So in essence, they actually move from positive charges to negative charge. That is the memory tip you need to get. Anything has to do with electric field lines, they move from where? The positive charge and terminate at the negative charge. So this is the correct option. Other options do not agree with what electric field line of forces represents. This is opposite it. And of course, they do not form closed loops around stationary charges in electrostatics. They do not cross one another because they actually move in a particular direction and terminate on the other. All right, so the correct answer is option C. All right, next question says, which of the following is a scalar quantity? Let me make a little correction. Which of the following is a scalar quantity? A says electric field intensity, B says electric force, C says electric potential, and D says electric what? Displacement. What do you think is the right option to this very question? Without even guessing much, electric field line of forces have direction and magnitude. All right. When you see the word force, anything that has to do with force has direction, of course, has magnitude and has direction. Electric, when you see displacement, is changing a specified direction. So, of course, it's also has direction. The only option here is electric what? Potential. All right. From the word potential, it's more like energy at rest. So if we are to define electric potential, it's actually the work done per unit charge in bringing one positive test charge from infinity to its rest point. All right. So this is option C is the one that is approved as scalar quantity. Next question says, a magnetic force on a current carrying conductor is maximum when the conductor is dashed to the magnetic field. What option do you think is correct? All right. The correct answer to this question is option B. Now, the key exam tips you need to understand is that the magnetic force on a current carrying conductor is maximum anytime the conductor is perpendicular to the magnetic field. If it is parallel to the magnetic field, then there's no force, right? There's no force on that particular body. And all of these angles are actually making it less than 90. So perpendicular here means that it is at angle 90, all right? It's at angle 90, that is sine 90. Sine 90, you know, is equal to 1. So, of course, the formula for force in a current carrying conductor is given as this. So if we have sine theta to be sine 90, because that is for it to be perpendicular, the angle has to be 90 degrees, all right? If the angle is 0 degree, then there will be no force. We therefore say it is what? Parallel. But they said maximum. So if they ask you for minimum, they say the current carrying conductor is minimum when, right? This would have applied. But that's not the case here. We're dealing with maximum, maximum force. So thank you. We're going to go to the next set of questions. All right. So the first question says that we have another question here. Which electromagnetic radiation has the highest frequency? We have radio waves, infrared radiation, visible light, gamma ray. Now, for us to be able to answer this question, I need to tell you that the electromagnetic spectrum, right, in order of ascending frequency, when we say ascending frequency, as in from the highest to the lowest. So I'm going to make a space here to just write something here that's very important. So in terms of increasing frequency, right, the first on this, okay, first we have radio wave from increasing, right? Radio wave, it increases into what they call microwaves. Microwaves, then we go into the infrared. At the infrared, we have the visible light. At the visible light, we have what we call the ultraviolet. And after the ultraviolet, we have what we refer to as the X-rays. And from the X-ray, we have what we refer to as what the gamma rays. So let me point out something that you need to know. Anytime you are asked the highest frequency, notice that radio wave has less frequency compared to microwave. Microwave has less frequency compared to infrared. Infrared has less frequency compared to what? Visible light. So in other words, if you are to choose which one has the highest frequency, it is from gamma ray this way. Now, microwave has less frequency compared to, radio wave has less frequency compared to microwave. So the highest frequency is gamma ray in terms of frequency, seconded to what? X-ray. So X-ray has higher frequency compared to ultraviolet, and ultraviolet has higher frequency compared to visible light. Now that is in terms of what? Frequency. But in terms of wavelengths, radio wave is the first, is the highest, seconded to microwave, third to infrared, like that. So if you ask a question that says which is the highest wavelength, you should consider it in this order. All right. But if you're talking about highest frequency, this is the highest guy. But in terms of highest wavelength, this is the person. All right. Now, in terms of the photon energy, gamma ray also has higher photon energy compared to X-ray. So the correct option to this question, what I've explained, is what? Option D, which is gamma rays. Hope you've learned something. So the next question that we're going to look at is, according to Bohr's model, an electron emits electromagnetic radiation when it's dashed, right? The first option says remain in a permitted stationary orbit. Second one says move from a lower energy to a higher energy level. C says move from a higher energy level to a lower energy level, and this is rotate continuously in the same energy level. According to Bohr's model, right, electron is only emitted, right, when the electromagnetic when it moves from what, from a higher level to what, a lower energy level. If it moves from a lower energy level to a higher energy level, it's actually absorbing photon energy. It is not releasing it, it's absorbing it so that it can actually increase in terms of its ascension. And if it rotates continuously in a stationary position, there will not be any form of radiation. And if it also remains in a permitted stationary orbit, there will still not be any form of radiation. So the correct option for this particular question, according to Bohr's model, is that for electron to emit electromagnetic radiation, it has to what, move from the higher energy level to the lower energy level. All right, we have to find the equivalent, the energy equivalent. So we calculate the energy equivalent of a mass of 2.0 milligram, and the speed of light is constantly, the constant of the speed of light is given there. These are the options we are given, and for us to determine which option is correct, we're going to solve using this formula. That's energy equivalent is equals to the mass times the speed of light in its squared. Is a formula I'm going to actually what, apply. Now, from what we have here, we have the speed of light already as 3 times 10 raised to the power of 8 meter per second. Our mass was given as 2.0 milligram, and we have to convert from milligram to what, kilogram. Okay, so for us to be able to convert our mass, we're going to do it as 2 times 10 raised to the power of negative 6 in kilogram. So anytime you are to convert from milligram to kilogram, you multiply it by 10 raised to the power of negative 6, right? So we can get our equivalent what, energy by saying our mass of 2 times 10 raised to the power of negative 6 times the speed of light, which is 3 times 10 raised to the power of 8, all in its squared. This is 2 times 10 to the power of negative 6 times 3 times 10 raised to the power of 8 in its squared. It's 9 times 10 raised to the power of positive 16. And then let's do 2 times 10 raised to the power of negative 6 minus 9 times 10 raised to the power of positive 16. Our answer is we got 18 times 10 raised to the power of 10. We can still go ahead to say this is 1.8, right? Now, we'll add 1 to this power because we have put it in one decimal place, right? Now, times 10 raised to the power of 11. And the unit of that is what? Is joule. It happens that our correct answer is option B. Question 17 says, when an electron moves from N3 to N2 in a hydrogen atom, the atoms dash A absorbs a photon, B emits a photon, C becomes negatively charged, D it loses its nucleus. What do you think is the correct option? I believe you will have guessed right. It happens that the correct answer to this question is option B. It emits what? A photon. And what is the principle behind it? When an electron moves from a higher energy level to a lower energy level, all right, there's going to be an emission of a photon. But if it moves from N2, let me assume that a lower energy N2 to from N2 yes to N3, it's going to actually absorb a photon, which is not the correct option. So if it's from a higher energy level to a lower energy level, it's going to what? Emit photons. So option B is the correct answer. All right, the next question now is say light or frequency below the threshold frequency falls on a metal surface. What happens when its intensity is increased? Now, for A says electrons are emitted with greater kinetic energy, B says more electrons, C says electrons are emitted after a delay, and D says no photoelectrons are emitted. What do you think is the correct option to this question? All right, so it happens that the correct answer is option D. No photoelectrons are emitted, right? Now, under what condition will there be emission in terms of this particular question. For there to be emission, our light frequency or our incidental frequency must be greater than our threshold frequency. But if the threshold frequency is, the light of frequency is less than the threshold frequency, no emission will occur. So making option D the correct answer. Last question here before we move to the next. According to Faraday's law, the induced electromotive force is proportional to the dash. A says magnetic flux, B says rate of change of magnetic flux, C says resistance, and D says initial current. If you're very familiar with the laws of Faraday's law of induced electromotive force, you should know what option is correct. So it happens that the correct option is option B. So the simple thing is that irrespective of the magnitude of the electromotive force, as long as it is constant, there will not be any induced electromotive force if there is no change in the magnetic flux. It is a change in magnetic flux that leads towards the induced electromotive force, very importantly. Go to the next. Okay, so we have two questions here we are going to solve simultaneously. The first question says the peak current in an AC circuit is 10 ampere. Calculate the root mean square current. Right now, the formula that will guide us, the options are 5 ampere, 7.07 ampere, 10 ampere, and 14.14 ampere. Right now, the formula that will guide us in solving this is simply the root mean square of the current is equals to the peak current all over the square root of 2. And look at the peak current we're given in this question is 10 ampere. So we'll simply just substitute 10 all over the square root of 2. And if you do that, the root mean square is equals to now 10 all over the square root of 2 okay. So the square root of 2 is 1.414, and 10 divided by 1.414 we have 7.07. Therefore, the correct root mean square is 7.07 ampere. So making option B the correct option. Next question says that two capacitors of 6 microfarad and 3 microfarad are connected in series. Calculate their equivalent capacitance. Anytime you see capacitors connected in series, now there are two formulas you can use in solving this. You can use 1 all over the capacitance of the equivalent, which is equal to 1 all over the first capacitance plus 1 all over the second capacitance. Now you can either use this formula, or you can actually say that the equivalent capacitance is equals to the product of the product of the two capacitors all over the sum of the two capacitors. Either ways, you still arrive at the same answer. So let us apply the two ways. Now, if you're dealing with this, you're going to have 1 all over the equivalent capacitor is going to be 1 all over the first is 6 plus the second capacitor is what? 3. Now, if we have that, we're going to have 1 all over the equivalent, which is, if you find the LCM of 6 and 3, it's going to be 6. 6 divided by 6 is 1. 6 divided by 6, 1 times 1 is 1. Plus 6 divided by 3, that's going to be 2. 2 times 1 is what? Is 2. So it happens that we have 1 all over, our equivalent is going to be 3 all over 6. And if we cross multiply, we're going to have 3 of the equivalent capacitance, which is equals to what? 6. So that if you do the equivalent capacitance, it's going to have 6 all over 3. And the equivalent capacitance is going to be what? 2 microfarad. So making option A the correct answer. Like I said, you can actually use, you can say that the equivalent capacitance is equals to the product of the two charges all over the sum of the two charges to give you the same answer. That's to say, you're going to say 6 times 3, 6 times 3 all over 6 plus 3. So if you do this, it's going to be 18 all over what? 9. And if you do 18 divided by 9, this is still going to give you 2 microfarad. So either ways, you're correct. So we have a question here from Radioactive Decay and Half-Life. And the question says that a radioactive sample has a half-life of 8 days. If its initial mass is 80 grams, calculate the mass remaining after 24 days. These are the options that we're going to look at for which of them is correct. Now, you can solve, all right, and perhaps arrive at this answer before I do. So it happens that the formula for finding the remaining mass of a sample after a certain period of time is given as N is equals to NO in bracket of half raised to the power of T all over T, where N is the remaining amount NO is the initial amount before it underwent radioactive engagement. Then T is the time elapsed, and this capital letter T is the half-life of this particular sample. Half-life. Now, from all indication, we are given we are given this. So we're going to actually look at all of these, and then we'll be able to find the amount remaining. Now, looking at this question, we are asked to find the amount remaining. Now, what was the initial amount before this particular radioactive sample underwent this particular phase? So they say it has an initial half-life of what? Of 8 days. So that's to say, if we're writing this half-life, we're going to write 8 days here. This is 8 days. If its initial mass is 80 grams, so the initial mass is 80 grams. Calculate the mass remaining after 24 days. So this was the time it was elapsed. So we're going to, first of all, I will tell you that you should look for this particular variable first, all right? And so the first you're going to determine the number of half-life, all right? So first of all, determine what the number of half-life, and number of half-lives is equals to the time elapsed all over what? The half-life. So which is equals to, time elapsed here is 24 all over 8. 24 divided by 8 is 3. So it has a half-life of 3 days, right? Now, we're going to actually input this into this formula and then get the answer that is correct. So remaining amount N is equals to, the initial amount is 80. 80 times 1 over 2 raised to the power of 3. That's all we got there. So this is going to be 80 times. Now, 3 times 1, 1 times 1 times 1 to 3 places rather, is 1. All over 2 times 2 times 2 is going to give us 8. All right, so this is going to be 80 divided by 8. So our amount remaining, if you do 80 divided by 8, is going to give you what? 10 grams. So the mass that will be remaining after 24 days is going to be what? 10. So our correct option is option B. Next, we're given a question that says that the electric field intensity at a point is E. If the source charge is tripled and the distance from it is doubled. The new electric field is. So what you need to understand about questions of this manner, now these are the options we are going to choose from. So let us solve. So you go ahead and solve as well. Remember that the electric field intensity E is given as the spring constant, the Coulomb constant times the charge all over the radius in its squared form. All right. So what we're going to do in essence is this. Based on what we're told that if, remember that this K is constant, so it is 1. Now they say the Q is tripled, so you triple Q. And then they say you will double R. Right? Now, of course, double R means 2R, triple Q means 3Q. So what will happen to the new electric field intensity? That's what we are asked. So we're going to say E, now this is the new, it will be equals to, and this is 1. Now remember, this is, let's just say this is 3Q all over, this is 2R all in its squared, right? So we have it that this is 3Q all over, this is 2R squared, is going to be what? 4R what? Squared, right? So the electric potential of the new is simply going to be 3 of the electric potentials all over 4. That's just going to be the answer. So the right option is option B, as it is. All right, we're told that 2-point charges exert an electrostatic force F on each other. If the first charge is doubled, the second charge is tripled, and the distance between them is doubled, the new force is. These are the options we are going to actually find out. You can solve as well as much as I do. So it happens that the force between two charges is given as this, Q1, Q2, all over R squared. And from our question, they said, what would be our new force if, now remember, K is not given, force on each other if the first charge is doubled. So let's say Q1 is doubled. So we're going to have 2Q1 times the second charge is tripled. So we're going to have 3Q2 all over. And the distance between them is doubled. That means this R, we're going to double R squared, right? So this is going to be, if you do 2 times this, it's going to give you 6K Q1 Q2. 6K Q1 Q2 all over. If you square this, it's going to give you 4R squared. So it happens that our new force is going to be 6 all over 4. And if you divide that, it's going to give you 3 all over 2 of our force, right? So if you're doing that, our new force is going to be 3 times F is going to be 3F all over 2. So it's going to be, I've got actually going to be 3 of the force all over what? 2. So it happens that the correct answer here is B. Next. So we have a question here that which factor determines the maximum kinetic energy of photoelectron emitted from a metal surface? A says intensity of the light, B says frequency of the incident light, D says surface area of the metal only, D says distance of the lamp from the metal, right? Now, option A, intensity of the light, option B says frequency. Now, let us look at this. The intensity of the light can actually increase the number of photons, right? But it does not directly affect or leads to determine the maximum kinetic energy of the photon electron. The surface area can actually determine how many photons strikes the metal, but it does not really determine the kinetic energy of photon that is emitted from that metal surface. The distance as well does not really. The correct option is the frequency of the incident light. That is what will actually lead to determine what the maximum kinetic energy of photoelectron emitted from a metal surface. You have to take cognizance of that very importantly. The next question says, what is the SI unit of magnetic flux? Okay, so the correct option is option B. So the next question says, what is the SI unit of magnetic flux? A is ampere, B Henry, C Weber, D Tesla. And now you all know that the ampere is a unit of current, Henry is the unit of inductance, Tesla is a unit of magnetic field. So the correct option is Weber. That is the unit of magnetic flux. So option C is correct. Next question says that a charged particle moves parallel to a uniform magnetic field. What force acts on it? Now, anytime a charged particle moves parallel to the uniform magnetic field, what you need to know is that the angle it forms is what we refer to as sine 0 degree, right? And if it forms sine 0 degree, it therefore means it is 0 because sine 0 is 0, right? So the correct answer there is 0. No force will act on this particular particle. So the correct answer is option A. All right, so we have a question here that says a magnetic flux of 6.0 times 10 to the power of minus 3 Weber passes through a coil of area 4.0 times 10 to the power of minus 2 meters square. If the magnetic field is perpendicular to the plane of the coil, calculate the magnetic flux density. And these are the options we have to pick from. I believe you can actually calculate and see to the option that is correct as well. Okay. So it happens that the formula for magnetic flux is equals to the magnetic field or the magnetic flux density times the area times cos of the theta. Now, we have to find this particular angle. Now, what will help us guide us to find this angle? Before that, let us start with, we are giving our magnetic flux as what? They say magnetic flux of, so 6.0 times 10 raised to the power of negative 3 Weber. We're giving our area as 4.0 times 10 raised to the power of negative 2 meters square. Now, for us to be able to find, we're looking for this right now. Our cos theta, since it is perpendicular to the plane, it means it is cos 0, right? So our cos theta is actually equals to cos 0 degree, and cos 0 degree is 1, right? Cos 0 degree is 1. If it was actually parallel, it's going to be cos 90, and cos 90 is 0. So we're going to actually solve this right now. Before we solve, we're going to make this the subject of the formula, all right? So here we go. We're going to say BA cos theta equals to the magnetic flux, so that the magnetic flux density is equals to the magnetic flux all over the area times our cos theta. And we substitute, this is going to be, this is 6.0 times 10 to the power of negative 3 all over our area is 4.0 times 10 to the power of negative 2. Of course, times 1, which we know is insignificant. So our magnetic flux density is given as, if we do 6 points in our calculator, 6.0 times 10 raised to the power of minus 3 all over 4.0 times 10 raised to the power of minus 2. It happened that our answer will be 0.15 Tesla. So our correct option is option B. All right, this is a question from capacitance, and we are told that a capacitor of capacitance 5 microfarad is connected across a potential difference of 12 volts. Calculate the charge stored on the capacitor. These are the options we are given. What do you think is the correct answer? I believe you're solving already. So let us go into the question proper. To solve this question, we'll need a formula that connects the charge with our capacitance and our potential difference V. So it happens that the charge is equals to CV, where this Q is a charge measured in coulomb, and C is a capacitance measured in farads, and V is a potential difference measured in volts. And so from our question, we are told to find our charge on the stored capacitor. Very simple question. So we'll actually say that our charge is equals to, what is our capacitance? 5 microfarad. But before we impute that into that, we have to convert this microfarad into farad. And how we're going to do that? Anything has to do in micro, you multiply by 10 raised to the power of negative 6. So this is what we're going to do right now. We're going to first convert. Okay, let us convert the capacitance. 5 microfarad equals to 5 times 10 raised to the power of negative 6 in its farad states, right? Then our volt was given as 12 volts. Therefore, our charge is going to be 5 times 10 to the power of negative 6 times 12 times 12. And so we're going to multiply that. And so 5 times 10 raised to the power of minus 6 times 12. So that is given as 6.0 times 10 raised to the power of negative 5 coulomb. That will be our stored charge on this capacitor. So it happens that our correct answer is option A. One more question, then for call it off. We're told that 3 capacitors of capacitance, 4 microfarad, 12 microfarad, and 3 microfarad are connected in parallel. Calculate their equivalent capacitances. Now, what you need to know is, once you see anything under capacitance that is connected in parallel, whatever is connected in parallel is simply the sum of their individual capacitances. So for us to calculate the equivalent capacitance, we're going to say equivalent capacitance is going to be the first capacitance plus the second plus the third. So it is simply 4 plus 12 plus 3, all microfarad. So this is equals to 19 microfarad, making option C the correct answer. All right, so we have come to the end of today's class. As regards what we've done thus far, one of the things I'll tell you is that don't just memorize formulas, don't just memorize the questions we've solved. You should understand the principles, the formulas that backs them. You should be able to understand their application. All right. Very, very importantly, convert where you need to convert, especially in terms of the SI unit. It really helps you a whole lot as you prepare for your exam. Most importantly, all the work we've done, there's still much more to do. But for today, we've been able to make progress in respect to what we've prepared thus far. And please, as we call it a day, don't forget to like, comment, subscribe, and follow us, and do well to share our videos across all our platforms. You could as well help a colleague of yours. Thank you very much, and always keep in touch for simplified tutorial sessions with Insight Tutorials. I remain your tutor, Peter Ogbaji. See you next time.